on that screen. So if you think about it, what does that mean? What do that position distribution? What it tells you is the following. You see, you have dropped all the lattice and the trap. The flight of these bosons is a free flight, right? Forget about gravity. That is not important here. It doesn't really affect the bosons that much. So the position of the screen after time t just depends on its velocity when it started, that is inside the trap. So the position distribution of the bosons in the screen is just a reflection of the momentum or the velocity distribution of the bosons inside the trap. So measuring this pattern on the screen, what is the momentum distribution of the bosons inside the trap just before you have killed the trap. That tells you about the quantum state of the bosons inside the trap. So how do you do this? For example, if I didn't have an optical lattice, this will be just a central blob here, showing that inside the trap, most of the bosons are concentrated in the k equal to 0 state. That's what is supposed to happen for a superfluid. Now, as you put in more and more of the potential, initially the central peak remains. There are some sub peaks because now you have additional periodicity because of the lattice. But around 13 or 14, when the energy depth is, in terms of some unit of energy, which is the recoil energy, that is, it's basically the natural energy unit that you can create out of the wavelength mass of the bosons. When this crosses a critical value, which is roughly like 14 times this recoil energy, the central peak is gone. And the bosons, we have all different distributions of momentum. They are completely delocalized in momentum in the trap because they are completely delocalized in real space on the screen, all sorts of momentum. And because delocalization in momentum space, localization in real space, think of your Heisenberg uncertainty. This is a state which tells you that the bosons are very well localized inside the trap. And this is a state which tells you that the bosons are in a superfluid state. So this transition from a superfluid to this insulator is essentially a MOT, and I'll tell you why MOT. It's a special type of insulator, superfluid. A superfluid to a MOT insulating system. Okay, is one of the first realization of observation of a phase transition between a state of matter, which is a superfluid, to another state of matter, which is a MOT insulator, using these platforms. And this, I can tell you, is very hard to do in a realistic, in a standard laboratory setup, because you here is a completely clean system, no disruption of anything because of disorder or any other external environment. And this is really finest examples of such a transition. Okay, so here are some cartoon pictures. This is how the the bosons fly out, and this is how they hit the trap. And I've already explained what it means. And more cartoon pictures from the Nature paper where they show one the boson superfluid state and in the MOT state. Okay, and so now with this experiment, let me explain the model which essentially describes this transition. Okay, and that's called the Bose-Hubbard model. So the Bose-Hubbard model has two ingredients. One of them is an on-site term, which tells you that have bosons on every side of this lattice, but in each side, if you put two bosons, they have an in them. So that's called the Hubbard interaction between them. And then there is a chemical potential which tells whether it's favorable to put in more bosons or less bosons in a given parameter range. These bosons can hop from one side to the other, which is a term which is just hopping of bosons from one side to the other. Now, if you look at these bosons, you'd see that if I have this chemical, this is actually mu. Some of the fonts got something. If this mu is between 0 and u, then if your hopping is very, very small, is a state with one boson per side. Okay. Just take my word for it, but this is real. But now, since I know that eventually if I decrease my lattice depth, which is which amounts to increasing this hopping strength, this state should go away. I can think of what happens, if I add so I can think of ways this mod state is destabilized. So one way of looking at this is that, this mod can have several excited states. And one such excited state is when you add a particle to this. Once you add a particle to this state, there is an energy cost for doing that, because now, because of these on-site terms, you put an extra energy of u, and you gain an energy because you have added an extra particle. So that energy is u minus mu. But now it's kind of free to hop around. It doesn't cost any extra energy because you've already paid that energy through u when you have added this particle. So it can lower its energy by this amount. T is, and z is something called the coordination number of the lattice, which is how many neighbors each lattice have. And therefore, when this beyond the critical value of t, where delta up goes to 0, the mod state is destabilized because the excitation energy becomes negative. So if you're doing a perturbation theory and your energy to first order perturbation comes out to be positive, negative, then you have done something wrong, right? That's basic quantum mechanics. And therefore, here it's just a signature of the instability of the ground state, that the ground state which you have started from is not the right state anymore. Okay. So you move a particle and then you get a critical value of this hopping, which is a bit different, but two is essentially gives you the critical hopping at which this mod state is destabilized, gives rise to superfluid. Okay. And this is one way to understand this transition, why that happens. Now, of course, this apparently can be, sort of sophisticated in a much more sophisticated manner. So people have considered higher order process. They have considered mean field theory, which was done by Fisher first in '89, and then TVR wrote a very nice paper on this. Quantum Monte Carlo studies, which was done by Nandini Trivedi and Krauth. And all of this essentially tells you that this model has a phase transition. And for people who know about quantum phase transition, this has a dynamical critical exponent of Z2, except at the tip of the Mott lobe. Okay, at the tip of the Mott lobe, what happens is actually this, that at the tip of this Mott lobe, these two hopping same. Okay, that's where the tip is. What does that mean? It means adding a particle and removing a particle, which were which had previously different energies. Now, they have energy. In other words, you've developed a particle hole symmetry in the problem, because adding a is different from adding a hole. The problem was particle hole asymmetric, but now there is an extra, and that changes your dynamical critical exponent. Symmetries can do that. It's known in the community, but the point is that there is a transition from Mott to the superfluid state, and this transition is precisely what the in cold, ultra cold packed forms showed. This thing was known since '89, okay, but first realization came in 2003. There is another interesting thing that one can do, and this essentially, I don't want to get into the details, but what you can do is that you can calculate the Green's function for these bosons in the strongly correlated limit. It's a slightly subtle calculation. You can do this. Essentially, what happens is that then you can, from the Green's function, you can compute expectation of anything. And here we compute the expectation of momentum distribution, keeping the experiments in mind. Apparently, what happens is that you see that as you go towards the superfluid transition from the Mott state, much before you reach the superfluid transition, the momentum distribution starts developing this peak, which diverges at the transition when you enter the superfluid state. It has a name. It's called the precursor peak to the transition, and this has been seen essentially in experiments by Bill Phillips' group in 2007. This precursor peak essentially, this precursor peak grows as you go towards the critical point, and there's some theory that we did was not too bad, essentially, looking at the data, and this had no fitting parameters. Okay. So yeah, so that's what I wanted to say about this transition model. So next, I'm going to talk about another system which is called the tilted optical lattice. So you can take these systems. The next thing you can do is what the experimentalists did to tilt this. And what so okay, let me skip through. Yeah, sure. Please go ahead. Ask anything that you want. Right. Yeah. So you see, this is sort of a momentum cut. Okay. So inside the okay. So where is this? Yeah. So this is deep in where V is 27 times this recoil energy. Okay. So you are really, really deep inside, and you see it's pretty much flat. Okay. These black dots are the experiments, and the red thing is the theory. Now you approach it a little bit, 17 year, you are still in the Mott phase, but you see the momentum distribution now starts to peak around k equal to 0. And you go a little bit around, this is sort of in the superfluid phase, but very close to the critical point. Momentum distribution kind of peaks out here. Okay. So as you approach, you develop this precursor peak. So that's the
So that means you are still away from the criticality. You are not.
No, here you are on the other side of criticality. Here you are a bit away from the criticality. The criticality is roughly around 14 or 13 year. Okay. So the question is, how do you apply this tilt, or what is called this electric field? So these bosons that people typically take are essentially neutral bosons. They don't have a, so they don't, when I say electric field, it's not a conventional electric field. I mean, it's not an electromagnetic field which couples to these bosons. But what happens is that these bosons, which is 87 rubidium atoms, they are always, almost always in a state of S equal to 1, or rather A equal to 1, some primary quantum number. And therefore, it couples to their magnetic field through Zeeman coupling. And if you can make a magnetic field which has a gradient, this term in your Hamiltonian, right? Because of the Zeeman term. If this Bx is just, and this means that it is equivalent for these bosons to have a scalar potential, because scalar potential corresponding to a constant electric field also gives you this linear term. To these bosons, this is just like a scalar potential. Okay. So this linear term in bosons constitutes a generation of electric field, quote unquote electric neutral bosons. Okay. So this is how this is done. This is done is that you can take this trap and move the, so that if previously this was a harmonic potential which is like half kx square, now you move its center, so this becomes like half kx minus x naught whole square. X naught is the shift, and then the cross term between x naught and another linear term. That's also like generating an electric field. Okay, so people with shifting the center, but later basically shifted to putting this magnetic field because this was easier to do in experiments. And here is an experiment. I'm not going to get through the details of this. What they showed is that applying this electric field, one can have a resonant response if you are deep inside the Mott phase, not in the superfluid phase, but if you are deep inside the Mott phase. So it so turns out that the value of this electric field out here hits a special value, units of U, that is the interaction between these bosons. There is a resonant absorption of energy. Means that it's connecting between some quantum states. So the one wanted to ask was, what is this resonant energy? Okay. We looked at this problem long time back, and so what we did is to effective 1D model, which was the simplest one to construct. Think of a parent Mott state where we start from, where it had two bosons per side, and then we tilt it by putting on either an electric field or a Zeeman term or whatever you want. And we are in the regime, the difference of this U and E, that is the interaction term here U, and this electric field E, and the Hopf W here, is much, much less than either the electric field or U. And this is a limit I would like to point out, which is never achievable in the laboratory. Because if you wanted to put an electric field this strong in a standard material, you are going to have electric breakdown much before anything else. So this is a sort of a new parameter regime in this kind of models, which you could have explored, which you could explore at that point using these ultra cold atom platforms, which you normally cannot. So, okay, so we had this mod thing, and then we wanted to ask that what are the excitations? Let me just get into this. So basically, if you put an extra electric field, these adding particles or holes is no longer low energy of the problem. That's because you pay an energy cost to add them, but then their hopping is constrained by this electric field. And if you ask how this extra hops, you can show that it has a hopping term, but this electric field. And this particular Hamiltonian is known as the one-year Stark Hamiltonian. It's called the one-year ladder. And it's known that all the eigenstates of this one-year Stark are well localized. Okay, so the boson is not free to move around, and therefore, because of it simply doesn't delocalize. Okay, what does delocalize are dipoles. So essentially, probably missing a slide. Yeah, slide here. These dipoles are bound pairs of electrons. Can I use the chalk, Phil? Oh, is there? Okay, thank you. Just it was a mathematician's class, so there must be a chalk. I'm pretty sure. So imagine that you had this initially. Okay. Now I think of, so let's just take one boson per side like this. Okay. So and I go to this configuration. Okay. Nothing here, a hole, and there are two bosons here. So these boson are just by one. So this pair of hole and boson, okay, this process energy U minus E, because you pay an extra energy U because now this boson goes and sit on top of the other boson. Hence an energy E because there is an electric field in this direction. Okay. This can still be a small number because we are in the limit U minus E. And it's basically these dipoles that are the smallest possible excitations of this problem. And what we did is to write down an effective model. It turns out that it costs an U minus E energy to create these dipoles. And then there is these dipoles which can happen because the bosons can spontaneously hop from one side to another. That leads to dipole creation or dipole destruction. And there is no conservation of dipole number. But there are two important constraints in this model. One, there is only one dipole out here. You cannot form a second dipole. The second one is that if you have formed a dipole in this link, the next link out here, this thing cannot go here, because if it did, it's an energy minus 2E, which can be large. Okay, that is not allowed. There is a constraint that there is no two dipoles on neighboring sides. Okay, with these two constraints, essentially explains this physics. Yeah. That will work even if you have more bosons per side, because the second dipole is going to cost an energy which is much larger than this U minus E. Yes, because the second dipole is going to cost more. So you can either have 0 or 1. The second dipole cannot be there. Okay. So yeah, so basically now let's just imagine what the phases of this Hamiltonian is. Forget about this term. Let's just think of this. You see, if this E is much greater than E, the ground state is a dipole vacuum. Okay, because there is a large energy cost of, and you don't want to do that. So essentially, everything is and that's a boarding state. Okay, it's a vacuum dipoles, which essentially means that it's the parent mod state where you started from. no hopping dipoles, nothing. Okay, but think of the strong electric field case where U minus E is a large negative quantity. Now what you want to do, form as many dipoles as possible in this ground state. But I told you that you cannot form dipoles on two neighboring links. So you can either form dipoles on the odd link or on the even links. So there are these two equivalent ground states, one with dipole on the odd links and another with dipole sitting in the even links, which could be possible. When the system chooses one of these, it breaks a Z2 symmetry. This is clearly like an Ising system where all spins can either point up or down. This is one ground state, which is like breaking the Z2 symmetry. So here we have a situation where you have a garden variety vacuum state separated from a Z2 symmetry broken, exactly like an Ising paramagnet or an Ising ferromagnet. And it's not surprising the transition in between when you analyze this belongs to the Ising universality class. And so we predict that there would be a Ising transition in this system. And much later, I'm again not going to details, people in Marcus Greiner's lab essentially looked into this, and they did see a transition, from from this paramagnetic state, which is this no dipole, to this state, and there is this nice curve. Of course, they cannot determine the universality class of this transition because that in an experiment. But I would be very surprised if this doesn't turn out to be Ising. Okay. So yeah, and there are even more dynamic experiments to this. One can move through this transition and back. In nice Stuckelberg oscillations, something that happens when you move through a critical point. Okay. So the bottom line about this is that tilting this optical lattice, second type of models, and it's one way of realizing this Ising spin model using this, using this kind of systems. And that's also something which is quite interesting. It's in, in standard experiments. Okay, how much time do I have? 10 minutes? 5 minutes? Okay, good. So I'm going to talk about this Rydberg atoms a bit. And then, yeah. No, this picture is not going to hold. But so, for example, if you apply something which is like, instead of a linear thing, if you apply something else, that doesn't have an interpretation in the lattice because it's not really a linear this thing. There will be some kind of potentials, and maybe one can analyze. But there is an issue that the higher powers that you take essentially has a better chance of destabilizing these systems, because systems are saved because of this one-year start ladder, where everything is delocalized. I'm not really sure what happens when you have a higher power of this potential actually. If it is X-core or things like that, I don't really know. Yeah. Here, yeah. Yeah. So, no, that's like having two separate dipoles. One on, okay, can I? So let's just take another link here, okay? And you are saying that this can happen, right? This is what you are saying, right?
Second and the third.
No, okay. Let me come to that. But first, this is your link 1. This is your link 2, 3. So this is like having two dipoles on link 1 and 3. Now let's come to the point. So let me just, you were saying something like this, right? Right?
Referring to the same item here, instead of pairing between third and fourth well, can we not pair between second and third?
saying this, so say this is the pairing between first and second, and now if this hops here, this is pairing between the first and third. That
Pair between second and third, like there is a electron in the second, orbital electron in the second,
yeah,
the hole in the third. So can we not pair the isolation?
this one you mean? No, if you have already paired this, you can show that pairing this is much more energetically expensive. Okay, this is going to work. And that's why this constraint that DL dagger DL is 1 to 1. Because if you do this pairing between them, that this whole thing costs an energy which is not in units of U minus C. You can think about this, if you do this, you are going to cost an energy which is U minus 2E or U minus 3 or something like that. Okay, which is on this low energy subspace. You can try pairing this and calculate, because it's all on site, it's easy to calculate, but it doesn't hold up. Okay, so let me just go into this Rydberg atoms. So essentially, these atoms, which another class of atomic systems, which essentially has caught our attention of a lot of people. These are 87 rubidium atoms coupled to their Rydberg excited state. What it means is these atoms have two levels, one ground and one Rydberg excited, with all the atomic details given here. And they are, so you take these atoms, you subject them to external lasers, which provide an effective coupling between this ground and the Rydberg excited stuff. Okay. And this coupling essentially depends on these laser frequencies with respect to the atomic levels, and these are typically called detunings. The difference between this blue and the red lasers, frequency added, and this energy difference between this R and G, that's your delta, that's called the detuning, which we use. Okay. Now these atoms have one interesting features, which is why they are. If you excite them into this Rydberg excited state, you do this between two atoms, both of them excited to the Rydberg excited state, they essentially show a huge van der Waals interaction between them, which goes R to the power 6. Okay, it's a property of these atomic levels, and once you put these Rydberg atoms on these levels, if you put two of them side by side, it costs an energy of the order V0. If you put two of them two sides apart, it by 32 and so on. Okay. So the point is that the Hamiltonian, which describes such a system, is very simple. For, if this delta is large, it's hard and positive. It's hard to produce, sorry, delta is large, and in this thing, if it is negative, it's hard to produce a Rydberg excitation. The lasers are simply not powerful enough to pump atoms from G to R. However, if delta is large and negative, well, large and positive rather, then it's easy. You can always produce efficient lasers to produce this. However, there is this other term that if you have put in Rydberg excitation on one side, then putting another Rydberg excitation on another side gives you this energy cost. Okay, Vij Nij, and this is the dipolar excitation. And then there is a coupling between this ground and excited state, which are the coupling strength omega, which is given by this, the product of frequencies divided by this detuning of the intermediate levels. It has some very complicated atomic physics. I'm not going to get into the details of this, but it gives you this interesting Hamiltonian one can analyze. Okay. Also here, V0 can be tuned, so you can make large enough so that Rydberg, for example, Rydberg excitation in neighboring sites are forbidden, but you can form Rydberg excitation in next nearest neighbors and stuff like that. And people have done this. So they start from a Rydberg vacuum state where delta is large and negative, okay, and there you do not create any Rydberg excitation. All the atoms sit in their ground state. into the positive delta regime, and suppose you tune your V naught in such a way that you block Rydberg excitation between two neighboring sites. Okay, if you do, then of course at large positive delta, the system is going to be to form as many Rydberg excitation as possible, except that they cannot do that. So they can form one at site 1, then 3, 5, 7, etc. There is a Z2 symmetry breaking because they could have as well done it on 2, 4, 6, and so on. And this Ising transition, what we showed for the tilted lattice, just shows up here. But here there is more because you can now kick up your V naught one notch further and prohibit Rydberg excitation on two neighboring sites, because both V naught and V naught by 2 to the power 6 can also be a large number. They can do this in the experiment. And there you see a transition to a Z3 order state. This belongs to the Potts universality class. And then Z4 order state and so on. This is all experimental data from Marcus Reiner's group, and evidence of these transitions in this kind of thing. And this model that we wrote down before can be mapped onto this model here. And I'm not going to get into the details of this, but the point is that it's a constraint with, so all of this can be mapped onto some kind of constraint spin model, which describes the low energy physics of this Rydberg atoms very well. So this is one way of realizing spin system, in this kind of optical lattice setup. And the reason why it is important becomes evident when you go, instead of one chain, to a two-dimensional thing. So essentially, in 2D, if you take some lattice like the Kagome here, you see that this kind of set spin liquid physics. This is Ashwin's paper. And there are some paper by Subir's group, which looked at it on the square lattice, giving rise to a lot of different ordered phases. And there is a zoo of such phases out there. So the point is that, if you take kind of spin models and you want to realize them on this optical lattice setup, Rydberg atoms provide a perfect platform. And you can really look into, and in coming days, I'm hopeful that they would be looking into more aspects of spin liquid physics. And this is one realization of this kind of systems. So I'm going to just take one more slide. And this is with dynamics with these ultra cold atoms. So these ultra cold atoms are very isolated systems, and therefore, whether or not they thermalize, as in prediction of ergodic statistical mechanics, has been an issue. And that people have looked into in different contexts. And I'm just going to sort of give you one of the first experiments that has been done. So as you know, when you sort of look at the dynamics of an integrable model as opposed to an integrable model, things are very different, because in an integrable model, there are lots of conserved quantity, and therefore they really do not go into a Gibbs ensemble upon thing. In integrable model, they do. So apparently there was, to test, in non-integrable model, they do go into a Gibbs ensemble, a thermal ensemble. So there were some early experiments, this was in 2006, to test this. So what they did is that they looked into a one-dimensional Bose gas. So it's a 1D lattice, and you put, and this is in a regime where it's mostly in a superfluid state. It's not in a lattice or anything. And then they provided an initial energy E to these bosons, and they at t equal to 0, you impart an energy, but because of this P2 minus P symmetry, you can have the momentum of these bosons at some large minus P and large positive P, each having the same energy. So the Bose condensate just splits up into two, and then they let this the evolution. So they come together and then again splits up, and they this for very long time without equilibration, as long as you can keep the system stable. Okay. However, and I don't have picture here, but if you do exactly similar thing with the 2D Bose gas, which is a non-integrable system, do the same thing on a 2D lattice, you'll see that after a few cycles, there is a thermal distribution of this Bose gas. Okay, so this clearly is an experiment which, through dynamics, through coherent quantum dynamics, showed basically that the integrable systems and non-integrable systems very different, and this is like a real experimental demonstration on one of the fundamental tenets of statistical mechanics. So there are many more dynamics with these cold atoms that has been done, that people are working on both theoretically and experimentally. But I'm going to stop here because it's late. And so let me conclude by saying that these platforms essentially are good platforms for emulating both strongly correlated models as well as studying coherent dynamics of systems. And in one expects that they're going to give rise to many more interesting features. We're now trying to use them for doing basic qubit manipulation and many other things, but probably another talk. So thank you for your attention.
Thank you, Professor Sengupta, for this nice overview on colded state of atom. So I will like to ask first online speaker. Please speak up if you have any question. Seems no, but in the meantime, we can take question from.
So you talked about mostly spins and bosons, but are there going to be
Yeah, but that's okay. So I haven't really talked about that, partly because of time. But the point is that people do that. So there are these many systems which do that. The problem with the fermions is that getting below the Fermi temperature for a bunch of fermions, getting to a temperature where these things are still coherent, has been a huge experimental challenge. Okay, and can do it. And the first thing that they wanted to look into is the Fermi-Hubbard model. Well, of course. There are some experiments in that direction, but no conclusive stuff yet.
Thank you, sir, for this nice talk. So I wanted to know how these electrons being displaced from the whale, as you said, like there is a shift between when you introduce the tilted model. You said that there are two ways this can be achieved. One is by introducing a specially very field, and the other one was by
Shifting the center of the track.
Yeah, shifting the center. How is this two thing giving rise to the same?
Okay. See, the point is, let me just try to explain this here. So, suppose you have a bunch of bosons. So these are not electrons; these are all bosons, and they are perfectly neutral. So imagine that when you have these things and you put them in a trap. So these bosons see the harmonic potential. So this potential is like, so first let's take this. So sitting in the trap. But now I take this trap and shift it center. What this means that I now have a something like this, right? So this means for the bosons is the original trap minus okay. This is just a constant, forget about it. But this, you see, is roughly like an electric field proportional to, because that's the potential. So shifting the trap gives rise to an effective electric field, as if the bosons has a charge which depends on this case. They are connected to this electric field. So the identification, of course, is that E and E star E is not. That's right.
So this arrangement also gives rise to this dipole arrangement.
No, this just gives you the tilted tree. And then the dipole is, of course, a theoretical structure. But later they found it in experiments that that thing. So so now these bosons are now in the stated trap. Now you ask the question that what happens if you increase this speed? The thing that what we did and then what people is that they go into a state where they have infiniteness. Okay. Meaning that you have a 0, 2, 0 rather than 1, 1, 1, 1. Okay, that's the dipole state. Okay.
Shifting of a boson from a well to the next well was because there was
because there was two things. Because there was an energy cost. If you put a boson in the next well, you put an extra energy U, and that there was a which led it to gain an energy E. Okay, some E, which is this E. Okay, because you go by one lattice size. So therefore, what happens is that when this U and E are close to each other, you go through a transition when E cross, this hop becomes much more
feasible.
fair. And then you can ask that why, you don't let it go through many lattice sites so that, you lower energy a lot more. And the reason for this is that constitutes an electric breakdown. And these systems do not have an electric breakdown at this electric field level. Everything is localized, but these states can be, because of the interaction, you can have two separate types of localized states. One of them has one boson per site, and the other one has this 0, 2, 0. That's the.
Yeah. Thank you, sir.
Any question?
Yeah.
Symmetry, right?
Which one? The tilted?
The tilted.
Yeah, that has a Z was.
I mean, I can see the effective Hamiltonian which you wrote down for the dipole which has that. And
Yeah.
then it breaks it, so it's
Sure.
kind of that.
But in terms of bosons, this is one possible ground state, and the other possible ground state is something like this. So let me map this state to here, but have this. So you see, this link is 0, 2, etc. This is 1, 3, etc.
Right.
So you can either have the hop here or have the hop.
Right.
So that original boson also have this that symmetry. Yeah.
Okay, any one? No. No question? Yeah.
Sir, here we used to trap that atom, na?
A magnetic field.
That
Yeah.
yeah. So we are not using the electrodynamic, like time varying electric field to trap that atom.
No, nothing is time varying here.
But we could have used electrodynamic ion traps, na?
No, because
Charge. Bosons do not have charge.
these are neutral atoms, so they don't couple to electromagnetic field with the standard E and stuff like that.
Okay. No question? No students? Okay. Let's thank Professor
Thank you.
Sengupta for this nice talk. And I would like to Sambudha to present the memento. Thank you.
এটা মানে আমার কিছু ক্যারি ব্যাগ নেই, মানে ক্যারি অন।
Thank you for joining.
No, there is no problem.
Always try to, but
Monday mid-semis class starting.
in the midst of everyone try to take some extra time to finish their course.
No, yes. I'm actually surprised that students get pretty late and also the mixing starting which
Hopefully seeing something.
Chalo.
Yeah.
So if we have multiple particles in the tilted lattice, it's not likely to move because there's an energy flow.
Yeah.
Right? If I have two atoms per side, but then one of them has three, it won't move because of. But then if I have a dipole forming next to it, then can we then see a dynamic of it moving?
No problem. So let me. You are saying. So suppose I have two atoms. That's my favorite one.
Yeah, I'm gonna have an extra.
Yeah.
Yeah.
Okay. Yes.
I happen to see some kind of a dipole formation here, where the whole thing. Can I see dynamic? There's still an energy.
No, there's because once you have added this,
Right.
it's kind of, what happens is that, this cost an energy of the order of no? For this, and of course, there is a minus B, but this is a positive energy. Now you see for these to move very well.
The E itself is an energy.
Yeah, is that these will have, okay, I can move by adding this term. The other B. But now if it moves here, then there is a E, right? Because if this thing is here, then it has gained that. Now this thing localizes. So that's the. So if this problem can be exactly solved actually.